Hi, my name is Dylan Weir, and today I'll be presenting my Tauranga Slope Stability Research and Development Project for the Maungatapu Peninsula. Landslides in Tauranga can be a severe threat to many communities, causing property damage and, in worst case scenario, can cause harm to people. The Maungatapu Peninsula is an area of significant interest, with the area being prone to multiple historic failures taking place along the coastal cliffs. This research and development project aims to investigate potential key soil parameters within the slopes and how they affect the slope's stability. To study the key parameters influencing the slope's instability, 5 distinct slope sites in the Maungatapu area were chosen for investigation and computer modeling of 5 different scenarios for both drained and undrained conditions were then completed. A desktop study was used as the preliminary study of the Maungatapu area to provide a better understanding of the coastal slopes topography, geology, and soil composition. From this study, 5 slopes were selected based on the following selection criteria. Slope topography. These slopes were selected based on their height and slopes cross-sectional dimensions. Historical failures. Slopes that showed any sign of previous failures were identified, as they may be prone to future failures. Additional features. This was applied to any feature that could potentially affect the slope's stability, such as current drainage conditions or the slope's vegetational cover. Based off the selection criteria, 5 slope sites were then chosen. These are shown by the red circles on the aerial image of the Maungatapu Peninsula, with the 5 locations being spread out across the Maungatapu area. Each slope's profile and corresponding parameters such as friction angle, cohesion, and unit weight were then found. Using LiDAR data and QGIS software, I was able to find the cross-section for each of the different slopes. Previous geotechnical tests such as boreholes and hand augers that were found near each slope were used to determine the layering of each slope. Parameters were then correlated from CPT and SPT testing data. The aerial images in this slide show the site's area along with the location of the cross-section. This is represented by the red line. The completed cross-section for each slope are shown below that. The purpose of each cross-section is to show the layering that is present within the slope and the slope's dimensions, along with the water table's height and the geotechnical testing data that was used for each slope. The final 2 aerial images and the cross-sections of the 26 Sunset Crescent slope and the 80 Harmon Street slope are shown. Site visits were carried out for the 5 slopes that were selected. This was done through an in-person investigation of each individual slope site in the Maungatapu area. The purpose of the site visits was to gain an improved understanding of any potential factors influencing the slope's stability. Shown in the 2 images are pictures taken from the site visits from the 446 Maungatapu Road slope. The top image shows the peak of the slope with a ridge circle showing the exposed slope face. This suggests previous failure has taken place on the slope, with the bottom picture showing the base of the slope. With the found correlated parameters for each slope, a slope stability analysis was performed for each of the 5 slope sites. This was done with Slide 2 software. For each of the selected 5 slopes, 5 different scenarios were run for undrained and drained conditions. The first scenario was a static groundwater table, which represented a base scenario for comparing other analyses. Next, a raised groundwater table was used to simulate a scenario where excess rainfall and flooding causes the groundwater table within the slope to rise. For both the static and raised groundwater tables, a 3rd and 4th scenario was completed, where an additional applied load was placed on top of the slope. This load represented the loading from houses that have been built on top of the slopes. The final scenario was seismic loading, where the slope was subjected to a load that simulated that of an earthquake. An example of the slide analysis results for the 446 Maungatapu Street slope are shown. Each quarter circle represents a circular failure plane, and at the top of each circle is its factor of safety. The distance from the slope's peak for each failure is also shown. The key findings from this investigation have been summarized. An increase in the groundwater table will have a significant effect on the slope stability, especially under undrained conditions. The impact of an implied load from a building has a minimal effect on the slope stability for both short-term and long-term conditions. During an earthquake event, the slope stability drastically decreases. Changes in the friction angle and cohesion have similar effect on the slope stability. Through sensitivity analysis of each layer within the slopes, the Matua subgroup layer was found to be the most sensitive layer. The topography of the slope had a significant effect on the slope stability, with steeper slopes such as the 446 Maungatapu Street slope having an overall lower factor of safety. Undrained short-term analysis of the slopes resulted in a higher factor of safety compared to that of drained long-term conditions. Thank you very much for listening to my presentation for the Tauranga Slope Stability Research and Development Project of the Maungatapu Peninsula.